So I'm going to start this video just like I would if we were in class. So we're going to revisit some of the things from that first video. I'm then going to add in one more additional topic related to panel data that I want to make sure we know how to work with. So got my path already set because I'm recording these videos back to back. I'm going to open up this file that I'll put on Canvas called GDP class data. So take a look at it. It's pretty basic. It's got income and unemployment rates. It's got different counties and different states across different time periods. So here I've just got a little bit of a unique example that we didn't look at last class, which is what is really my observations here? It's not every single state, right? It's going to be every single state and county, right? Those are my subjects. The problem is that's not built into like one variable. I've only got county and then state. So it'd be ideal if I had another variable that was a unique number, not for every state and county, but for every state-county combination. So here's kind of our naive regression. We're trying to figure out what's the effect of income on unemployment rates. Looks like as income goes up, unemployment rates go down. That's not surprising. But there's probably going to be some important omitted variables, and we can't control for all of them, but we can control for anything that's time or subject invariant. So the first thing we're going to do is say, okay, let's try to set this up as a panel data set. We kind of talked about in the last video, we can use XTSet. Now, the problem is if I try to use multiple variables here, there's too many. That's not how XTSet works. However, I know that my subjects aren't each state or each county. It's each, because there could be the same county name in different states. It's each unique combination. So what I can do is something we haven't really looked at yet, and it's kind of fancy. I might not expect you to kind of do this on a problem set, but kind of showing you, usually Tuesday's classes, I try to keep it a little more basic. Thursday, I add in some things the second half of the semester that would be kind of next level. So by each state and county, we're going to create this thing I call unique. It's a new variable, and it's going to be equal to 1 for the first observation of every unique state and county combination. So I'm going to run this and kind of show you what this is going to do. So for every state and county, for the first observation, 2011, it put a 1 in there. For every other observation, it was a 0. Then with the next county, a 1 for its first observation. I'm now by this unique variable, right? So only the very first year for every county. Create this state county ID, which is _n. So all that does is say, once I've kind of separated these up, for the very first county, put in a 1, the next county, put in a 2, 3, 4, 5, etc. So notice for all the zeros, it didn't do anything. But for that year of 2011, oops, and it kind of does it, you know, alphabetically, or not necessarily, actually, no, it doesn't do it. It does it by these numbers here. So I've got a 1 represents Otsego County, Michigan. 2 represents what? Rensselaer in New York. I'm not sure how to pronounce that. McCreary in Kentucky is a 3, so on and so forth. So here, how many unique counties do I have in my data set? 2,953. All right. Now that I've got that variable created, well, I want that same number to be there, not just in for 2011 for Fumas, Nebraska. I want it to be there for all of these other years as well. So I'm going to go back to saying, okay, by this state and county, take the maximum value of this variable I created. Well, if all these are missing, the maximum values will just be whatever year was in 2011. So now, Teton, Wyoming, for every single year, has 184. For what? United, Wyoming has 378. So every county now has, sorry, every state county combination now has their own unique number assigned to it. I can now use this as my fixed effects variable, right? So now I don't have to just control for the state or just for control for the county. I don't have to use multiple IDOT commands. I'm controlling for the state and county combination by using this new variable I created, okay? Just as a kind of be complete here, and I'll put it in up here. Probably should have done this to begin with. We said, how can we see if this is a balanced panel? Well, let's just create this variable that's equal to a 1, right? Could also say, I'm then going to generate total years variable, which was the sum of my count variable, and then take a look at it and make sure every single one hopefully should be, how many years do I have in this data set? Looks like 1, 2, 3, 4, 5, 6, 7. So we'll kind of run this code. Oh, what did I do wrong? I forgot to put a space here. So we'll kind of hit there. Sure enough, well, that's not right. Why is that not right? Because I forgot a very important thing here, which was by sort. Oh, I can't do this after this. So we've already created this variable state county. So I probably should have put this below it just because we have to create that first. Okay. That's not what I wanted. Hold on. I'm on the wrong line. I'll get there eventually. There we go. State county. So I'm going to put this down here because we had to create that state county variable before we check to see if it's balanced. All right, so now let's just run all of this again. Once again, I was showing you can't run two, so we had to create that state county variable. Is it balanced? Sure enough, looks like every state county combination here has 7 years of data. Okay. Now, one thing, if I were then to set this panel data set, so instead of doing this every single time, if I use the xtset command and my subjects are state county, the time is year, notice it will tell me that it's strongly balanced, right? So it doesn't tell me that it's exactly like perfectly strongly balanced, but it does kind of suggest that I don't have any missing. I don't have some state counties with only like 2 years of data or 3. Right? However, I can always manually check it kind of using this method. So I've got a nice, perfectly balanced data set. I've set it up now so that my subject is state county. So when I include this fixed effect, it's really like the same thing as using the I state county command. Right? So just to kind of show you here, I could use unemployment rate and income, I state county, right? Now, if I try to do this, this is going to take a very long time to run. Why? Because there's like 20,000 different dummy variables here. In fact, I probably shouldn't have done this because I might have just kind of crashed data here since I'm working off of IU anywhere. What would be better and what I wanted to do, well, I'm going to stop this because it's going to just take forever, right? So I can't really, run when I've got 20,000 dummy variables. It's just going to take Stata forever to do this. However, if I wanted to use the same exact regression, but I use my xtreg and kind of include those fixed effects, Stata is a lot more efficient with that command and can run that very quickly. So it doesn't show you that those dummy variables are included. So that's part of why it runs so much faster. It doesn't have to kind of output all of these additional coefficients for you. So we don't really want to do this. We want to use that xtset combination with that xtreg. Now, just like we talked about in the last video, we can also do two-way fixed effects, right? So if I were just to include fixed effects for the state county, I would have this as my estimate between income and unemployment rate. So it looks like it's strongly statistically significant, -0.24. Here, what is this doing? Well, it's controlling for anything that doesn't vary across time for my subject, my state county combination, but this I.year would then control for anything that is the same across all these county state combinations, right? So in the same time period. So this would be things that might change year to year, but they're the same for every single county. So this would be like national laws. This would be, the recession, if it impacts every county the same. So this is going to be a lot more powerful of a statement we can make with this regression because it's controlling not only for time invariant factors within these state counties, but it's controlling for state invariant factors within the same time period. So we can go ahead and run that, right? And what we see is, oh, well, if I can control for these things that don't vary across these subjects within the same time period, now I get not a negative coefficient, but a positive coefficient. Why? I've eliminated some of the omitted variable bias, right? So the whole, long story short, with these fixed effects, we're essentially just eliminating omitted variable bias. Okay. All right. So the next thing that we're going to talk about, and we won't get into the too nitty-gritty of this, but suppose that we have these independent variables and that they, sorry, I had my laptop sitting up here in the bag and it just fell. So if we have any type of correlation with our error terms across these time periods, which seems likely, right? It might be that the errors we're making in, whatever county in Alabama might be the same in 2000. There might be factors that errors kind of related to the error that we made in 2006 versus 2007. We were going to have this issue of the fact that our regression is going to have some heteroscedasticity, that our error terms will be impacted by the actual values for X, right? So the actual values for income here I had, because we were, I think, trying to predict unemployment. So we can't use the typical robust command. We said it was really easy before to solve this heteroscedasticity issue because we could just use the robust command, because it will not correct for the fact that we have autocorrelation in our error terms across these time periods. So we have a test for this to see, okay, do we have this autocorrelation in our errors, right? So our null hypothesis will be that there is no autocorrelation, right? So if there is no autocorrelation, that's going to be our null hypothesis. If we can reject that, we're saying that there is, right? And that our standard errors, right, aren't going to be right. We have a way, instead of kind of using this robust command, it's called clustering our standard errors, right? That accounts for this, okay? So the steps of doing this test for autocorrelation, we'll look and see what it looks like in Stata here, is I'm going to run my first difference regression. So like that first difference regression that we looked at in the last video. And I'm going to obtain my predicted residuals, right? Or the errors that my predictions were making from the predicted Y and the actual Y values. Now I'm going to do this and run a regression of those residuals on the lagged residuals, right? So skip this here for just a second. We're then going to test to see whether or not the coefficient on the lagged residual, when I run this regression, if it's anything other than negative 0.5. Okay? So if you find that it's statistically different, you have autocorrelation. So if you don't have autocorrelation, it would be exactly equal to 0.5. So that's what we're kind of starting out assuming, right? That there is no autocorrelation, where the correlation between our error term is 0.5. So maybe to kind of say this differently, our null hypothesis here essentially is going to be, is that correlation between the errors in this time period and the time period before, we're going to assume that it's equal to negative 0.5. If we can reject that, this was no autocorrelation. What we're really saying is that we have autocorrelation in our error terms, and that we want to somehow control for that, right? So how do we do this? Stata, right? So that kind of should end the slides here. The rest of what we're going to do is work in Stata. So the example I have here, we're looking at that unemployment income again, right? So how can I test for autocorrelation in the error term? So here I'm just going to go back to setting this, make sure my panel data is set correctly, right? So what I'm going to do, anytime I have this my data set set up as a panel data set, so this is going to tell me my state county combination by year, excuse me, I can use these capital L dots. And what that's going to do is it's going to say for every single state county, take the current year's unemployment rate and go back 1 year, take the unemployment rate from that year and subtract that. So L dot stays within the same subject, or here within the same state county, but looks back one time period, right? So I'm going to do that for both unemployment and income here. So just to kind of show you what that's doing. So for Oswego, Kentucky, well, my very first year of data, what's going to happen? I don't have a year before that. So when I try to use that LDOT command, it has a missing value. So when we run these autocorrelations, we're essentially going to lose that first year of data in a way, right? We aren't going to have, be able to go back one time period. But for every other year, what that, we'll do unemployment rate, that change in employment, it takes the current unemployment rate, subtracts the previous years, which would give me what, negative 0.4? Or down here, just to have that example of a positive one, takes the current unemployment rate, subtracts the previous year, puts in that value of 0.2. So capital L dot just looks at that same variable, but back one time period. Ignore this for a second. I'll kind of come back to this here. So now that I have this difference, this was essentially my first difference, right? I had the data set up differently in the last video where we had it kind of as separate variables, so it made it a little bit easier. But if I have panel data set where I've got multiple points in time, this is going to be how I create my first differences, right? So you can kind of think about this. These are my first differences, right? Well, we said part of this test was to first obtain those first differences and run a regression with them. So I'm going to run a regression where I'm using that first difference in unemployment rate and income, okay? I'm then going to, we've used this before. Now, generally, we've used this to predict different values for Y. We can also use this predict command. We then want to create this new variable. I'm going to call it the residuals. This is the errors that we were making from our actual and the predicted, the actual and predicted Y values. But instead of XB, which is what we usually use to make predictions for Y, if I tell this predict command residuals, it's going to store in this new variable the errors, right, or the residuals, the difference between the actual and predicted Y values. So I'm going to do that. I'm going to show you. Okay, it's got my residuals in here. So it made a prediction based off the unemployment rate and the coefficients, right, for what my actual Y value should be, what my predicted Y value should be. It then took the actual Y value, took a difference between the two, and then put in the residual over here, okay? So we're now going to use that LDOT command again. So the next step was take a regression with those residuals and the lagged residuals, right? Or the time period before's residuals. So take my residual variable, regress that on my lagged residuals. Now we're going to include no constant. So this is just something that we need to do when we're running this type of test. So this tells my regression, don't include a constant. We usually wouldn't want to do this in any other regression, right? We always wanted to have that intercept coefficient. But here, when we're looking for autocorrelation, there is no intercept, essentially. I'm then going to cluster these standard errors. So really what this is doing is, without getting too in the weeds, it's accounting for that there might be, it's allowing the variation to, it's allowing for the variation in my residual values to vary across state county combinations. So I won't kind of hammer you on this, but know that we need this line of code. We need to be clustering, what we call clustering our standard errors when we're performing this test. So I'm then going to run this regression. And I get this coefficient on my lagged residuals. Now I can kind of hear what these results always are going to tell me. Remember, anytime I run a regression, the null was that my coefficient was equal to 0. Well, that wasn't part of our test. We said we needed to have, is that coefficient different than negative 0.5? So we're going to run that test command. Usually, if we just run test without anything, it's going to use that kind of null hypothesis of 0. Here, we want to use the null hypothesis of, is it different than negative 0.5? Or essentially, is it equal to negative 0.5? That's our null. Can we reject that? Okay. So here I've got a p-value that's 0, so I definitely can reject it. Or I found very strong evidence, right, that I can reject that there's no autocorrelation, or said differently, strong evidence that there is autocorrelation, right? The null being negative 0.5, that meant that there was no autocorrelation. So I can reject that at very high levels, right? My p-value is 0. So I found I found that there is evidence of autocorrelation. Okay. So once I know that's the case, right, what do I want to do in my regression? So I don't want to simply run this regression. And actually here, well, I can kind of run both these lines of code and kind of show you what's going on. So we've got, here's a regression where I controlled for the year even. I'm looking at the unemployment, and why do I want that? I don't want income difference. I just want the actual income value. There we go. I just wanted income. Sorry about that. Must have hit the auto thing. So same kind of story. We get the exact same coefficient. But notice what's happening to our standard errors, right? Before, when we didn't what we call cluster our standard errors, they were much higher than after we cluster them, right? So after we kind of cluster these standard errors, right, our standard error on income went from 0.0019 to 0.0029. Or sorry, I said they're higher here. They're higher in the second regression because we're accounting for the fact that there's different variation within these states, right? So we're now getting much more accurate representation of what these standard errors should be. So notice if we don't cluster our standard errors, my p-value is a little bit smaller. So without clustering standard errors, we're more likely to reject when in fact we shouldn't be, or make type 1 errors, right? So we want to make sure we're clustering for these standard errors if there is autocorrelation, in which we found here pretty strong evidence that there was. Okay. Now I think I've got a second example here where I'll kind of show you how to use this ddot command as well. I just wanted to use a different data set just to kind of make it so it's not too stale. So I had this regression where I thought about, I wanted to look at traffic fatalities. So this was all mortalities from traffic accidents. And then what the beer tax in a state was, okay? So I'm gonna run that very naive regression. Looks like the beer tax is higher, there's more kind of traffic. Okay, that seems kind of weird. You would think that higher beer tax, people are less likely to be drinking and driving, you'd see fewer, but we might have some omitted variable bias. So one of the things is, well, if I set this up as a panel data set, and I've got different states across multiple time periods, right? It may be that there's things that are time invariant across those states that I want to control for. I've got an omitted variable bias. So I'm going to set this up as a panel data set. The subjects are my states, time period is years. I'm then going to include these fixed effects, which remember, it's fixed effects for whatever my subjects are. So here I'm going to run the same regression, but now my coefficients interpretation will be the effect of a 1 unit change in beer. I think it was a $1 additional in beer tax, would change the expected traffic fatalities in this state by whatever the coefficient is, holding constant the state, right? Once again, BYU might look very different, Utah might look very different than New York, right? So I'm going to kind of run my regression now, and whoa, I don't get 98, and it's not statistically insignificant. Now I've got negative 471, highly statistically significant. And that's because I've eliminated a large amount of important omitted variable bias. So the next thing we might want to check is, okay, is there autocorrelation in my error terms? So I showed you this way that you can do this using that LDOT command after you set this up as a panel data set. There's also another kind of helpful command, I don't know, just a little bit less typing. You can use this ddot. So what ddot will do is it takes this variable and it subtracts within the same subject after you've set it up as a panel data set. It'll take the mortality and traffic, traffic fatalities here, or traffic mortalities, minus the previous years. And then take the current year's beer tax minus the previous year's beer tax for that specific state. So once again, when we do that, for the first year that we have for every single state, what should we see for these variables? Well, we don't have any information from 1981, so we'll have missing values there, right? But for every other year, we can calculate what that change or what that difference was. So the ddot command is a little bit, I don't know, I think it's a little bit easier than using, where is it, that take the variable minus the LDOT of that variable. It's all it's really doing, right? Just kind of shorthanding it. So once I have these differences, we said we're going to run that first difference regression. We're going to obtain our residuals. I'm going to call this residuals 2. Now, when I was showing you in the previous example, if it helps, you can always type out residuals to let you know, oh yeah, this predict command is obtaining the residuals here. You can also shorthand it by simply using R. So if I do that there, okay, it's created these residuals. Now it's telling me I'm creating missing values. Oh yeah, because I'm essentially losing the first year of every single state here. So I've now got my residuals, right? We said part of this Wooldridge autocorrelation test was to then take those residuals and regress them on the lagged residuals. And that's the variable I created, was called residuals 2. Right? I'm going to include no constant in that regression and cluster my standard errors at the subject level, which was my states, right? So subject time, that's how we define these panel data sets. I'm then going to test to see whether or not the coefficient on that lagged residual is equal to negative 0.5, okay? Well, I've got a p-value of 0, so once again, I can strongly reject this null, or I found that there is a covariance between these residuals that is not negative 0.5. So if I can reject, I found strong evidence that there is autocorrelation. So I should be a little bit skeptical of the results I saw here in terms of their statistical significance. Well, not here. There you go. Here, in terms of their statistical significance, because there's autocorrelation across the time periods in my error term. How can I control for that? Well, I can kind of cluster my standard errors, right? So this was the regression where we just included fixed effects. Here we got, what, a test statistic of negative 4.85. Once I run that same regression, use my fixed effects, but I now cluster my standard errors at that state level. That should account for any autocorrelation that exists across these time periods. Well, now I end up with that. Keep going. Same coefficient, right? However, instead of negative 4.85, my standard errors are now going to be a little bit larger, and my statistical significance is a little bit lower. Now, in this scenario, even after clustering for my standard errors, I can still reject the null here, right? I can still reject the null that beer tax has no impact on traffic fatalities, but I can't do it at as high of levels. Now, here I can still do it at the 1% significance level, right? My p-value went from 0 to 0.007, but in other instances, this might flip my rejection decision. So we can use this test to see, is there autocorrelation in my error terms? If we reject this test, we need to make sure we're clustering our standard errors, okay? So that should be all of the issues kind of related to the panel data. It'll kind of round us out, take us into Thanksgiving break, and we will pick up on instrumental variables when we get back. Now, I also wanted to mention one thing, so to kind of incentivize you maybe to watch these videos, I will put up a little replacement for an in-class quiz. So we're going to have 10 of these by the end of the semester. And for that in-class quiz, I will likely ask you some of the things that we talked about in this video. So to make this a little bit easier, one of the things that I want to hammer on is, what are our typical fixed effects regressions controlling for? So remember, we said these fixed effects regressions, we've got y and x that vary across time and subject. There might be some factors that are time invariant. So when we use these fixed effects, we're essentially controlling for anything that is time invariant, okay? The other thing, another question that I might ask you is, once we have these fixed effects regressions, right, or the output, how can we test for autocorrelation? So this null hypothesis for whether or not no autocorrelation existed was the covariance of our error terms in back-to-back time periods, t and t minus 1. We assume it's equal to negative 0.5. That means that we would have no autocorrelation. So our null for that Wooldridge test is that the covariance of our error terms across these two time periods within the same subject is equal to 0.5. That would represent no autocorrelation. That's our null hypothesis, okay? So those might be two questions I put in that in-class quiz that I put up with the videos. Other than that, should kind of take us through panel data, and I will see you guys after Thanksgiving break.